Now we will prove two important theorems involving Poisson brackets. The first theorem is, we consider two sets of canonical variables, QP and capital Q, capital P. They are two different sets, interchangeable, meaning we can write small q in terms of capital Q and capital P, similarly small p in terms of capital Q and capital P. And on the other hand, this capital Q can be written in terms of small q, small p, and that is true for the capital P. Now, the Hamiltonian, suppose, is already given in terms of small q and small p. Now, if we just substitute in place of small q and small p the above relation, then this Hamiltonian will be a function of capital Q and P. So, it will be like a function of new canonical variables, and we will call it H tilde. After all, they are same. It's just a change of variable through substitution. If that happens, then the theorem says that Qi, Qj, the capital Q's, they will have the same Poisson bracket relation as the small q's, identical relation. It is easy to prove. I mean, take the capital Q, say ith capital Q. So, Qi dot, the capital Qi dot, you have ddt of that capital Q, and then you expand this time derivative as using the chain rule. And remember, in our transformation we have not included time. So, we are assuming that such transformation does not explicitly involve time. So, as such, the total derivative of Q does not have any partial derivative does not have any explicit derivative with respect to time. So, it is only with respect to Qj and Pj. So, we have del Qi, del Qj, Qj dot, plus del Qi, del Pj, Pj dot. Obviously, we can replace the Qj dot and Pj dot using the Hamilton's equation. And after that, we can do a little more algebra. This Hamiltonian, remember, we can simply write it as H tilde, where H tilde is the Hamiltonian, it's a function of capital Q, capital P, the new canonical variable. In that case, this partial derivative can be expanded in this form, that del H del Qk, capital Q, times del Q del Pj. And similarly, the other part would be del H tilde del Pk, capital P, and then del Pk del Pj. So, if all we did is we wrote H in terms of the H tilde, which is a function of capital Q and P, and then we expanded it using the chain rule. So, for the other derivative also, we expand it, and then we rearrange the term. We take the first term from both the bracketed quantities, and we take del H del Qk, and we see the coefficient of del H del Qk is simply the Poisson bracket of Qi Qk, and the coefficient of del H del Pk is Poisson bracket of Qi and Pk. Of course, we are keeping the subscript to denote that we are doing everything in terms of the small q and small p. So, there are quite a few lines. I'll just repeat shortly that take the new coordinate, take its time derivative, expand it using chain rule, use the Hamilton's equation of motion, and then this Hamiltonian is same as the new Hamiltonian using the new coordinates capital Q, capital P. So, a further chain rule can be applied when you encounter this partial derivative here. That is what we did. And then just we rearrange the terms to get back the final result, that we write this time derivative qi in terms of two Poisson brackets. Now, if you look at the previous expression, del h tilde del qk, this is by definition is negative of pk dot. We are using Hamilton's equation of motion using the new Hamiltonian. And similarly, we replace the del h del pk by qk dot. And then it becomes extremely simple. You have qi dot equal to two Poisson brackets and with their respective coefficient. Now we can compare the coefficient of q's and p's. Of course, the coefficient of p must vanish because we do not have any other pk dot anywhere else or pi dot. And when we compare the qi dot and qk dot, the coefficients, it is straightforward that qi pk, this Poisson bracket, must be delta ik, such that when I is equal to k, then it becomes 1, and you have qi dot equal to qi dot, it becomes an identity. Otherwise, it must vanish. It must vanish because the qi dot, and here we have qk dot, so there is no identity for any other coefficient, any other index. If it does not match, then the qk dot has only one occurrence. So we establish two important rules, and these rules are identical to what we have seen using q's and p's, the small q and small p. So we just proved one part of the theorem. For pi, we can start with pi dot, and that will give us pi and pk. You can just check it. It's extremely simple, the same algebra. The other theorem says the value of a Poisson bracket is independent of the choice of the coordinates. So what I mean to say that so far, whenever we were writing the Poisson brackets, we were adding a subscript q and p to denote that with respect to which variables are we taking the partial derivatives. But this theorem says that such a subscript might not be required, because no matter what you choose for the Poisson bracket, the value of the Poisson bracket is independent of your choice of the canonical variable. So again, as before, let's choose two sets of canonical variables, small q, small p, and capital Q and capital P. And let us suppose they are all interchangeable and time does not appear anywhere. We are talking essentially about scleronomic system, and small q can be represented using the new coordinates and vice versa. They are interchangeable. Now, again we have a long algebra. Look at this. The Poisson bracket of f and g, where f and g are two arbitrary functions. Okay. This is the Poisson bracket, del f del q, del g del p, and then del f del p and del g del q. What we do is next that this g, we can write it as a function of small q and small p, where we can substitute small q and small p in terms of capital Q and capital P. As such, the g here, it becomes a function of new coordinates, the capital Q's and capital P. So we can expand this partial derivative using the new coordinates. If we do that, then what we have is del g del qk times del qk del pk, and similarly for p part. So one part is with capital Q, the other part is with capital Q. We are doing the same thing here. Just replaced G using the other coordinates, the capital Q's and capital P's. Then, just like the trick in the previous theorem, we rearrange the terms. So, for example, we take the first term here, del G del Qk, we take it out, and what we have is del F del Qj and del Qk del Pj. Then we take the term, first term from this bracketed quantity here. We have del G del Qk, that is out. So we have del F del Pj, del Qk, del Qj. And we have similar set just by rearranging the terms here. And this gives us del G del Qk times a Poisson bracket of F and Qk. Similarly, we have del G del Pk times the Poisson bracket of F and Pk. And we kept the subscripts intact. Now, this is an identity. Identity in the sense that we have not dropped any term, we have not done any approximation. So, for any general F and G, we can always write this. Now, suppose we replace F by Qi, then what we have? We have Qij Poisson bracket, and that should be equal to, we use our previous identity. So we already know Qi Qk here would be 0, and here Qi Pk will give us delta Ik, and delta Ik times del G del Pk sum over k. We must not forget that there is a sum over k. That will give us del G del Pi. So Qij is equal to del G del Pi, and similarly Pij, the Poisson bracket, gives you minus del G del Qi. But I mean, this is with G, but it could have been, we can get the same thing in terms of F also. In fact, we can simply replace G by F here, because G is an arbitrary function. So whatever applies for G applies for F too. So it would be Qif would be del F del Pi, and Pif would be minus del F del Qi. These expressions we can substitute upstairs here. So you see we have Fqk. Fqk would be minus del F del Pk, and similarly we have Fpk. Fpk Poisson bracket would be del F del Qk. So if we replace that, we just did it there, and then you see we got a new Poisson bracket of F and G, but with respect to Q's and P's, the new Q and new P. So you see, we just proved the theorem that Poisson bracket with respect to small q, small p root coordinates or any one set of coordinates is identical with respect to another coordinate. So we are switching from one phase space to another phase space, and this small qp and capital QP, they are interchangeable. We have the relation. In that case, it doesn't matter which coordinate we use. The dynamical quantity f and g, any two dynamical quantity, their Poisson bracket is what we call invariant under such transformation. Poisson brackets have some formal properties, which most of the properties follow directly from the definition. They are antisymmetric. So Poisson bracket between f and g is negative of that between g and x. Of course, I mean that is straightforward. You write down the Poisson bracket and then just bring the g and f. Just write them in the opposite order, and then automatically it follows. And similarly, Poisson bracket of a function with itself vanishes, and because in such cases the two terms of the Poisson bracket would be identical and they cancel each other. They are linear, multiplied by a scalar, and if you add two dynamical quantities C1 F1 plus C2 F2, where C1 and C2 are constants and F1 and F2 and G of course are general dynamical variables, then we get C1 times F1G plus C2 times F2G. These Poisson brackets are, these properties are, you can get them just by substitution. Now, there exists a null element also, in the sense that Poisson bracket with any constant is 0. If it is a constant, then its partial derivative with respect to any coordinate will vanish, and as such the Poisson bracket vanishes. And the product rule similarly can also be established. The Poisson bracket between F and then G times H is simply G times the Poisson bracket of F and H plus the Poisson bracket of F and G into H. One easy way of remembering, you can remember this, try to keep the order of the Poisson bracket intact. So here I first take one of the function out and write down the Poisson bracket using the other, keeping F at the beginning, F, H, the order must be kept same, otherwise there would be a change of sign. And when we take the other function, we push the H the other way. Now this is not quantum mechanics, it really doesn't matter whether we write G after or G before, but it is a good idea to write it this way, keep the order of G and H same, that G on the left and H on the right, because if we keep doing this, then in quantum we do not have to relearn the precedence of the operation. Now final property, Jacobi identity, it's basically a cyclic rule. If you have three dynamical quantities, F, G and H, then this nested Poisson bracket, F and then Poisson bracket of G and H, then G and then Poisson bracket of H and F, then H and Poisson bracket of F and G, all these together, that gives you 0. Now, this is the proof of those properties are so elementary that I am not proving them. It follows quite straightforward from the definition of the Poisson bracket themselves. We look at integrals of motion using Poisson bracket. Let's consider F a dynamical quantity, which in general a function of generalized coordinate, generalized momenta and time. And if we require this to be an integral of motion, then its total time derivative must vanish. After all, an integral of motion means a quantity is not changing with time, so its time derivative vanishes. But we have seen that using Poisson bracket, the rate of change of a dynamical variable can be written as its Poisson bracket with Hamiltonian plus its explicit time derivative, del f del t. Now, if it is an integral of motion, then it follows that its Poisson bracket with Hamiltonian plus del f del t, that explicit partial derivative with respect to time, that must vanish. So one such case we can ask this question whether Hamiltonian as a function, whether it's an integral of motion. So for that we look at the total time derivative of the Hamiltonian, and that must be equal to the Poisson bracket of Hamiltonian with itself, and plus the partial derivative of Hamiltonian with respect to time. Now the Poisson bracket vanishes, Hamiltonian with itself. So the total time derivative of the Hamiltonian remains equal to the partial derivative of Hamiltonian with respect to time. So that means if the Hamiltonian is not a function of time, that means the partial derivative vanishes. In that case, Hamiltonian is an integral of motion. So, in many scleronomic systems, we have discussed that the Hamiltonian is not an explicit function of time, and for all such cases, it remains an integral of motion. So, in general, if a dynamical quantity is not an explicit function of time, then it would be an integral of motion if its commutator, its Poisson bracket with Hamiltonian vanishes. The reference to commutator is, of course, quite relevant. It happens in quantum. In quantum mechanics, if we have operators which are not explicit function of time, then we will see later that whether the expectation value of that operator changes with time or not depends on whether the operator commutes with Hamiltonian or not. But before we do that, we prove Poisson's theorem. Poisson's theorem says that Poisson bracket of two integrals of motion is also an integral of motion. So if you know two integrals of motion, then you know how to get the third one. Very easy, just take the Poisson bracket, just calculate the Poisson bracket of the two integral of motion, and you've got your third integral of motion. So let's prove that. It is straightforward. Suppose f and g are two integrals of motion. And then we can say that hf, the Poisson bracket, is equal to del f del t, and hg, Poisson bracket, is equal to del g del t. They both follow from the definition of integrals of motion. Now, we use the Jacobi identity, where the third function is Hamiltonian. So we have f, and then g, h, and then cyclic permutations g, h, f, h, f, g. Okay. But then g, h, that Poisson bracket is del g del t, with a negative sign, of course. And similarly, h, f, that is del f del t. Then these two terms, it is easy to rearrange them to get del del t of f and g, Poisson bracket. So from these two terms, we get del partial derivative with respect to f and t, and the remaining term is already the Poisson bracket of this f g with h. So if we define f and g, the Poisson bracket, to be another dynamical quantity, then say a, then we have del del t of a is equal to Poisson bracket of h and a. Then by definition, a will have to be another integral of motion. So fg, the Poisson bracket, is another integral of motion, and this proves. Now we look at some comparison between classical mechanics and quantum mechanics. Now we just define Poisson brackets. So in classical mechanics, we have a dynamical quantity f, which is a function of q, p, and t. In quantum mechanics, an analogous quantity is the expectation value of an observable. An observable is a Hermitian operator. Then in classical mechanics, what we have as a Poisson bracket, in quantum mechanics, that same rule is played by a commutator, except the scaling factor 1 by IH cut. In classical mechanics, the Hamiltonian plays an important role because it gives us equation of motion. In quantum mechanics, similarly, the Hamiltonian is an integral part of the equation of motion. In fact, it defines the equation of motion. H psi is equal to, the time derivative of psi, and with these factors. Okay. But here H is an operator. Then in classical mechanics, the rate of change of a dynamical variable is given in terms of the Poisson bracket and partial derivative of the quantity with respect to time. and that exactly matches with the Heisenberg's equation of motion, where we are looking at the rate of change of expectation value of an observable O, and that is given by the same Poisson bracket. We moved I from below to up, so that takes care of this negative sign there. Otherwise, it's exactly the same equation. So you see, what we are doing now in terms of Poisson bracket, it tells us that the classical mechanics, whatever we do in classical mechanics, it has an analog in the quantum mechanics. After all, quantum mechanics was developed borrowing the ideas from classical mechanics, and with also the expectation that there should be a correspondence. Actually, that gives us the correspondence principle, that whatever we calculate classically, the quantum mechanics should predict the same behavior for the expectation value. For a single measurement in quantum mechanics, or keeping track of a single observable in quantum mechanics, is of course probabilistic. But if we look at the expectation value, then that should be equal to the deterministic dynamics given by the classical mechanics, and that is what we get from Heisenberg's equation of motion. So entire development of quantum mechanics was largely motivated by this mathematical structure of classical mechanics and the demand of this correspondence principle.